Hello everybody, my name is Srinivas Agniparthi and my partner's name is Krishna Banda. So we together as a team worked on LSTM neural networks for predicting residential energy consumption. This paper has been already been worked or it's currently work under progress by Dr. Su and Dr. Remdi. And I along with Krishna Banda worked on few of the enhancements to this existing paper in the perspective of doing some micro level analysis on the existing data sets. So here is the outline that we are going to walk you through this PowerPoint presentation. So first we'll be going through the introduction and a few of the backgrounds, and followed by the implementation and the debugging, and then followed by the results, and finally observations and discussions with few of the references that are used while preparing this paper. So energy consumption prediction, what exactly does this mean, and how this can be used or helpful? So energy consumption prediction is becoming more popular research topic as many countries wants to know the requirements of the power consumption so that they can generate sufficient power to provide uninterrupted electricity. And for this paper, there are a couple of data sets that were used for the analysis. And the first data set is being used, which was being used, is collected from University of California document repository on the homes in the France. And the second data set, which is about the temperature of the Paris, was collected from the website MeteoBlue. As per the research, high levels of the accuracy were achieved from deep learning models. Even though there are quite a few deep learning models available like the CNN and RNN, LSTM is proved to be more efficient when it comes to getting the predicted results. So this paper mostly concentrates on the LSTM process. Different attributes are used from the data sets for the training the model, which I'll be showing in the next slide. As I already mentioned that there are a couple types of data sets that were used for this analysis. The first data set is which was used from the California's document repository. Has different kinds of parameters that were passed for training the model, the date, time, global active power, global reactive power, voltage, global intensity, along with three different kinds of submeters. Each corresponds to a specific appliances for the home. Like submeter 1 is something which takes the reading from the kitchen appliances such as oven, microwave, and the dishwasher. Submeter 2, which takes the readings from the laundry room, such as appliances such as the washing machine and the dryer. And finally, the submeter 3, which takes the readings from the air conditioners and the electric water heaters. Along with this data set, we also used a temperature data set, which has two different parameters in that, like date and time and temperature. So these two data sets were overlaid on each other to get an accurate results how the external temperature will affect the power consumption of a specific households. And after this, the later part will be taken care by my partner Krishna Banda. He'll be walking you through how the implementation is done, followed by a few of the results. Thank you.
Hello everyone, this is Krishna Banda. As Srini mentioned, like we work together with like Professor MD and Professor Su on an existing research paper to enhance some of the publishers like comments. When it comes to implementation and debugging of this the paper, so these are the things we have worked on, the enhancements and implementation of the existing research paper. The analysis of the temperature data transformation and merging energy consumption and the temperature data sets together, and projecting temperature data along with the power consumption data of submeter readings 1 to 3, and the total submeter readings and the global active power. We also worked on tuning the model, the LSTM model, which is a neural network, the long short-term memory model, with various dropout parameters, and including like multiple dense layers, introducing the dense layers. We trained the model with multiple parameters. Earlier, it was with one parameter, which is a global active power, and we also predicted the results and captured all the error results like MSER, MSEMA, and MAPE. In the next slides, I will show some the analysis details. So this slide, you can see the first part of the picture. The graph is the temperature data for 2 years, just like a time series projection. So this is like the hour and the minutely data, every minute data for the Paris, the city temperature. So you can see, the temperature for the summer months actually goes high, and then the January, December months actually goes down. So you can see actually it is like, the changing temperature over the years. The below one, the second graph is the daily average temperature and the global active power, the daily average. So this is projected over the years. Since actually the temperature, the measures are like, in 70, 30, 40 and 50 degree Fahrenheit, whereas the global active power is just like, 4 unit, 5 unit. So in order to actually make the graph, we just converted the temperature into 10 times of like any unit. So in the graph, if you see like 3 means the temperature is 30 degree Fahrenheit. So you can see the temperature and the global active power. In the summer months where we have the temperature is high, the active power consumption is little low. So we will also see like in a more detail in the next slides. So this is the observation part, and like the deep analysis. So this is like the monthly average of the temperature versus the total submeter readings. So you can actually clearly see in January and February months the consumption, they are like the energy meter reading is high, and when it comes to the summer months, June to August, the consumption is low, because like in the winter months, the especially like the submeter 3 consumes a lot. It has the electric water heater and the heating system in the home. So in the European region, especially Paris, like in the winter you have to have like more heating equipment, the heating system running. So that's why your consumption is high. When it's summer, it's like normal room temperature is sufficient. So that's what you see in this graph. And this one, so little more detailed. So in this graph, we projected all the submeters, like the submeter 1, 2, 3 readings, along with the global active power and the temperature. Again, the temperature here is like 10 times, or 10 times of each unit on the y-axis, which is like degree Fahrenheit, and then we have projected this like all the years from 2007 to 2010. You can see the different color lines for each different the reading. So submeter 1 is in green, and submeter 2 is in maroon, and likewise. So you can actually correlate like temperature is like direct relation with the submeter 3, where the temperature is um, when the temperature is high, the submeter 3, the usage is low in the months of like the June, July, and August of each year. Um, so this is little more. This is a daily average for all the parameters I just described a while ago. So submeter 1, submeter 2, submeter 3, and the total submeters along with the temperature. This is the daily average for all the years projection. In this enhancement, the tools and technologies for the implementation, we have used like pretty much like a Python programming, and then we have used various libraries. These are not like the exhaustive list. So these are some of the important libraries we just like showcased here to show you what we have used. Some NumPy, Keras, scikit-learn, and Matplotlib plot library, and there are many modules used in it. Main implementation is on the Jupyter notebook, where you can write the code and quickly run it, and then you can see the graphs and everything. The LSTM model is the neural network model we use. Code snippet is provided here just to know, the model, what kind of model we created, and the what are we passing the train data set, and also the optimizers used and the metrics added to the model. So when we compile the model, and also the number of epos, so 20 we used, and each batch like we have used at least like 100 the values. So yeah, this is the simple code snippet. The This is more about the results. So as we mentioned, like part of the enhancements we work towards, like to tune the model by changing various dense layers. We started with like dense layer 1, and then increasing to 2, 3, 4, and all the way to 10, and then captured all the time, like when we change the dense layers, when we add more dense layers in the model, how the MSE RMSE results comes better. So we have noticed like around 4 and 6, like the better results. So this is the train results, train data results, and this is the test data results. And you can see the train loss and test loss. Initially the train loss was a little high, and then over the period of time, once we progressed multiple epos, we used like 20 number of epos. So then that become like the loss become very stable, and the test loss is like in even it started like little less, and then over the period of time, like, or like the model is being exercised for multiple epos, it is like pretty static. That is what expected. um, this is just to show you the graphical representation of the mean square error and root mean square error and the mean average error results, where we have like multiple dense layers used, like how the results have been changed. um, This is another one. This is just like how for each time step, like the actual versus projection, actual versus the prediction, the results. So they are like pretty close. So that actually like good for like good model, when you're like actual and prediction are pretty close, means you don't have like much deviation. That's one another results you can see here. The references, like we have used like various the reference papers, at least like we have gone through 10 to 20 paper, I think 15 to 20 papers, all the paper details and other details references are provided in this slide. That is pretty much it. Yeah, I'm wrapping this up, and yeah, that's it.